Okay, so I'm going to go ahead, and we're recording today too. We're live. We're starting a new section today, 4.2. So if we take a look at this, what's your favorite website in the world? There you go, Corpy's World. So down here, they're those fine gentlemen again. That'll be all next year. Yeah, for sure. So today is Wednesday, right? So today we're going to explore applications of exponential and logistic functions. And your goal is to then write an equation of a real-life exponential function, okay? And some of y'all have already gotten that, all right? So that's what we're doing today. And here we go. We're going to jump in with example 1. 4.1 was all about learning about exponential functions, what they were, what their graph looks like, their characteristics, their properties. But 4.2 is now putting them to use, right? And whenever you put something to use, applying a mathematical equation to the real world, it's called mathematical modeling, right? Is that the kind of modeling? You could. I don't know if there's a career for like math models where you walk on the runway with a calculator, but that's not what this modeling means. This means we're going to use an equation to model real life behavior. And there's some limitations when you apply a mathematical equation to a real life situation. So here we go. It's your lucky day. I'm giving everybody fake $100. Yeah, here you go. Now, unfortunately, you can't spend it, right? Because you need to invest it. You need to do something wise with it. So here is a great deal. With your $100, you're going to invest it into an account that is going to increase by 30% every year. If you can ever get that as a guaranteed rate, would you take it? Yeah. Heck yeah. Heck yeah, you would. Okay? So, again, this is your lucky day. If you just look at that, aside from the chapter heading, how would you know that this is an exponential situation? Increase is one, but can we have things increasing that are not exponential, like quadratic? It's kind of funny. In the last week, I have heard the use of exponential growth misused twice. We talked about that in 4.1. I didn't go to the football game last Friday for like the first time in 15 years, so I listened to it on the radio. And I love Mr. Friesen who calls the game. But in the second half, he was like, the offense of the Unicorns has really picked up exponentially here in the second half. And I was like, no! I hope my students are hearing that and cringing like I am. I almost called in, but it wasn't a call radio show. Okay? And then I heard it again. She's not here yet. We're still expecting her. So I'm going to hang on to this maybe? Yeah. And then I heard on ESPN, they were doing the same thing. Some guy was talking about the defense of a team, what picked up exponentially. And I was like, oh, was that really exponential? No, because remember, exponential says the more you have, the more you get. Is that necessarily true? The more offense you have, the more offense you get? No, because defenses make adjustments, right? That's not necessarily true. But is that true with money? The more you have, the more you get, right? The rich get richer, especially when it's being increased by a what? What's the giveaway? The percentage. Good. Because remember, anything that increases by a percentage or by a scale factor. We talked about mitosis, meiosis. If something doubles every so often, that's going to be exponential. Same thing with percentage. It's really two sides of the same coin. If something increases by 100%, that's the same as what scale factor? You get twice as many as you had before, right? So a 200% increase is the same as a scale factor. I'm sorry. If you increase by 100%, it's the same as 2, doubling it. Good. So these are two sides of the same coin. So that's how you know it's exponential. There's a percentage there. So here's what we're going to do. We want to predict how much there's going to be in general after T years, which means we want to come up with an equation. Now, what mathematicians do, if anything, is they find patterns. We're good at finding patterns. And the holy grail is to come up with a formula that we can then use to predict. But in order to help ourselves see patterns, we start with concrete situations, okay, finite situations. So let's go ahead and do that. Okay, I want you to go through this if you already know what the model is. At t equals 0, when I first hand you your fake $100, what is the amount A that you currently have? Just at t equals 0. Here's your $100. Boom, you have $100, right? All right, so after 1 year, at t equals 1, we're going to let A equal the amount. How much do you have now? You have 130 bucks. How did you find that, Mr. Coronado? Uh-huh. And then what'd you do with that 30? You didn't say 30, you said 130. So what'd you do with that 30? You added it back. Yeah, very good. So y'all know how that works. If something increases by 30%, you're going to have everything you had before, the 100, plus another 30% of that number, right? And how do we write 30% as a decimal? 0.3, right? Percent means out of 100. So percent is 30 over 100, which, of course, you learned at some point you could just move the decimal 2 units to the left. So this is what you do when you spend money somewhere. This right here would be equivalent to your subtotal, right? You ever get the bill and you pass it to someone? This would end up being like the tax. Now, thank goodness we don't have 30% tax, right? And then when you add those together, you get something called the grand total. So like on restaurant receipts, that's where you usually see it. And then it gives you like, here's a recommended gratuity, right? 30%, whatever. Well, guess what? I'm not interested in this being $130 because mathematicians want to look for a pattern. And so let's look at it from this perspective. I have 2 terms. What do I have in common with both terms? A 100. Let us factor that 100 out from both terms. That leaves me a 1 plus 0.3. Yeah? Now, what is 1 plus 0.3? 1.3. So that is the amount that I'm going to have after 1 cycle. I have 130%. That's what that is as a percentage. The 100, the 1, is everything that you had previously plus an additional 30%, right? Now, if you're interested, yeah, he said that was equal to 130. I'll just take his word for it. Okay, let's go ahead. We're still investing at year 2. How can we figure out the amount that we currently have? Well, some of y'all are going to say dollar amount, right? I don't want a dollar amount. So how did we calculate it on the line before? It was everything we previously had plus 30% of that same amount, and we added them together, right? Let's do it again. Here's what we have on the line before. We have 100 times 1.3. I'll use parentheses here. That's how much money we currently have, plus another 30% of that. So I'm going to take that amount, 100 times 1.3, I'm going to multiply it by 0.3. It's the same idea. Everything we had before, plus that amount times 30%. Now again, instead of like coming up with a number, what do I notice that is in common in both terms? That, right? So if I factor that out, 100 times 1.3, I'm left with 1 plus 0.3. Well, look what that becomes. That becomes 100 times 1.3 times 1.3. Oh my goodness. That's the same as what? How can we write that? If I have 2 factors of the same, it's that number squared. Okay. This is getting interesting. Let's go one more time. I think I perceive a pattern. Do you perceive a pattern? Kind of slowly, maybe. Let's go one more time. You go as long as you need to create a pattern. So now the current amount in year 3 is going to be the previous amount, which was 100 times 1.3 squared, plus 30% of that, right? So that's 100 times 1.3 squared times 0.3. And again, we'll do our little trick. We have a common factor there. So if we factor it out, we're left with a 1 plus another 0.3. Wow, that's going to give us then, we can go straight to this, 100 times 1.3 to what power? To the third. So now if you're not seeing the pattern, let me help you see it. When t equaled 1, let's do where here it is. When t equals 1, we ended up with 100 times 1.3 to the first power. The pattern that we're trying to see is when I affect the independent variable t, time is the independent variable, how does that manifest in the right-hand side? Well, when t equals 1, it's 100 times 1.3 to the first. When t is equal to 2, it ended up being 1.3 to the second power. When t is equal to 3, it ended up being 100 times 1.3 to the third. Okay. So now let's work straight down here with ellipsis points. Dot, dot, dot. Can you predict what the model would be then for any value of t? Call it for t equals t. The amount should be what? 100 times 1.3 to the x, right? But we're going to use t instead of x because t stands for Texas, right? Time. There you go. Time. Good. Time. It's our independent variable. Let's see if that works. It should work for all values of t, right? Let's verify it for t equals 0. Because at t equals 0, we only had 100. What do you get when you plug in a 0 here? What's 1.3 to the 0? 1 times 100 is, yeah. So that does work up here. If you want to go back and add 1.3, it would be to the 0th power. Yeah, the pattern works. Should we go back in time? Should we go to t equals -1? Is that going to work? No. Very good. Okay, and that's where we get in the difference between the domain of the function that we're going to use to model this and the model itself. It might have a different domain. We call that a relevant domain. In this case, we're starting the clock as soon as we invest the money. So if we were to look at this function here, first of all, how would you know it's exponential now? There's no percentage in here, but yeah, we have a variable exponent, right? And the base is what? Greater than 1. So this would be an exponential what? Growth. This is an exponential growth function. The 100 ends up being the what? What do we call that? The y-intercept of the graph. It's the initial value of our investment, okay? So let's go ahead and sketch that. That function should look something like this. We're starting at t equals 0, which is at $100. And then from there, it's increasing by a factor of 1.3 every single integer value of t. So that is the part of the exponential graph that we're interested in, right? The graph itself would live to the left. I'll show that with a dotted line. So there still is a horizontal asymptote there. So the domain of the function is all real numbers. Well, what's the domain of our equation? What's the relevant domain? Oh, that's an A right there. Greater than 0 or what about at 0? Greater than 0 or greater than or equal to 0? Should be greater than or equal to, right? Yeah, because we include t equals 0. That's when we start. So there you go. That's the difference between a mathematical equation that might have a domain of all real numbers and a mathematical model that we're using to fit the situation. Okay, we call this right here the relevant domain. Relevant domain. The values of inputs, the time values that are relevant for the situation, whereas the equation itself might have other values that are not relevant. Okay, so sweet. Now that we have that, go ahead with example 2 and see if you can figure out what the I wanted to say one last thing here before we do that. This method here, when we first established the pattern, it required us knowing the previous amount, didn't it? We had to keep taking the previous amount times 30%. This is called a recursive pattern. A recursive pattern. You probably know a recursive pattern pretty well, the Fibonacci sequence, right? It starts with a 1 and a 1. Those are the two seeding values. And then to get the next number, you just add the two previous. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, so on and so forth. That's the Fibonacci sequence. It's a recursive sequence because it requires the previous numbers to get the next. There is no golden formula for the Fibonacci sequence, okay? But the holy grail in mathematics is if you can describe something recursively, that's great and all. But what if I wanted to know how much money I had at time 500? I wouldn't want to sit here and do this thing 500 times, right? Oh, bother. Or maybe back in the day before social media, there was nothing else to do, and you're like, cool, right? We want to say, okay, does there exist a Holy Grail formula? Okay, you can call that a formula if you want, into which we can just plug our value and compute it right away without having to do it recursively. And we just found one. You can just plug a 500 in here and save yourself some time. Time that can then be spent doing bigger and better math problems, right? So we found it. Not all things in the mathematical world have formulas. They can only exist recursively. Okay, so now what I want you to do on example 2 is see if you can come up ultimately with the formula. If you have to start with a recursive pattern to get you going, that's great. You're starting with another $100. Here you go, more fake $100 bills, everybody. But this time your amount is decreasing by 30%. It's not a wise investment, is it? I want you to come up with the model that will allow you to get the formula for the amount of money you have left at T years. I'll give you a minute or two. Use what we learned on example 1. Is that 0.7? Mm-hmm. Oh, make your decimal a little bit more prominent. There you go. There you go. Good. So you went right to it. That's good. Some of you are going right to it. You went right to the first one. You're the king. Yeah. There's the recursive pattern. That's good. Yes, yes. I did it from here. We did. Are you okay with how we did this? Okay, so when I factor the 100 out, what do you get when you factor 100 out of itself? 1. What do you get when you factor it out of here? 0.3, and then I added them together. So what this represents is 130%. No, because we're decreasing by 30%, right? So what would you lose in the first year? Instead of gaining $30, you're now losing $30. So you're not going to build money. You only have 70 left. So it's going to be smaller. It still involves the 30, but it's getting smaller now. You can, but that's the wrong base. Okay? That's the right base. Yeah, and then you can compute that. That's right. That's right. Yeah. Okay, good. If you've kind of spoiled the fun and looked down below, that's fine, I guess. But we're discovering the pattern here. All right, most of y'all are getting the model, which is great. Let's go ahead and just do 1 or 2 little recursive things with it. Let's start at t equals 0. We got the amount A is $100. Bless you. At t equals 1, though, the amount now that we have is everything we had before, but now because we're losing, it's going to be not plus, but minus 30% of 100. That's 100 times 0.3. So again, if you want to just calculate that, that's fine. We want to look for a pattern. So if we factor the common factor of 100 out, we're left with 1 minus 0.3. And again, you can verify by redistributing, right? Guess what the most common mistake is right here when people factor 100 out of itself? They want to call that a what? Instead of a 1, they'll call it a nothing. They'll just leave it blank. So remember, if you start with 2 terms, you're going to have 2 terms when you factor out. Well, what is 1 minus 0.3 now? 0.7, okay? And I think from there, you could probably infer what the model is. For any value of t, the amount should be the starting value and then times what would be the base? 0.7 to the tth power. Good. Now this is obviously exponential what? Growth or decay? It's decay. Because the base is 0.7, which is between 0 and 1. Now this should be intuitive to you. If we lose 30%, the base is 0.7 because that is what's left, right? So here's an example you could probably all appreciate. You're in the store, you're walking along, you find something you like, and it's like, hey, it's 20% off today. Have you ever stood there and calculated what the price of that would be at the register? Or do you just say, they'll find out at the register for me? Or have you ever calculated it? You have, right? What do you probably do? Who wants to share? How do you figure out the price if it's 20% off? Ooh, see, that's the advanced way. Awesome. But he is wearing the crown today. Very good. Most people would do it the same way we did up here. They would say, okay, if it's $100 and it's 20% off, then I'm saving 20%. I'm saving $20. So now it's $20 off, and then they go 100 minus 20, which is $80. But the faster, quicker way to do it is if you have 20% off, you are only paying for what percentage of it, Mikey? You're only paying 80% of it. So that is what the base is. If you're losing 30% each and every time, you're only retaining 70% or 0.7. So that's a real quick way to do it. Okay, so next time you're in the store, try to calculate it with one calculation instead of two. Okay, because remember, this tells us what the amount is at any given time. So if you were to sketch that one, your starting value would be up here still at 100, but now it's decreasing like that. And our relevant domain is still everything greater than or equal to 0. There would be other stuff over here that we're not interested in, right? Now, for you, if you didn't get out of that investment, would you ever run out of money? No, all right? The model says that if you wait like 5,000 years, if you live that long, you'll still have some change in the account, right? Maybe fractions of pennies, okay? But anyway, you can recognize the loss and get out of it. So there you go. That's growth, and that's decay. When you gain, it grows. When it loses, it's decay. So here's the summary. The exponential growth and decay model. The amount A, if it's changing at a constant percentage rate R. So we're going to let big R be the percentage rate. Okay, that would be our 30% in both of the examples. If that happens each time period T, then here is the model. We're going to let the amount at any given time be A, and notice it's a function of time. T is the independent variable. We usually used A in standard transformation form to be the y-intercept, but now we're going to put a little subscript on it. This is A sub O. That's how we read it, A sub O or A sub 0. And you have experience with that in physics, right? That means the initial amount, or the amount at time 0, the initial amount. So maybe in physics you call it like V sub I, the initial velocity, or V sub O, the velocity at time 0. So that's the initial amount, and it's going to be 1 plus R. We should add a little sign right here. It could also be 1 minus R. And some of y'all over there had the minus. So it's going to be 1, which represents 100%, and then plus or minus little r. What do you think little r is compared to big R? Big brother, little brother? If big R is the percentage rate, little r is nothing more than big R expressed as a decimal, right? So if we look at our example from number 1, we had the amount at time t. The initial amount was 100, and it ended up being 1 plus 0.3 to the tth power. So big R was 30%, but what was little r? 0.3, right? And in example 2, we had A sub t. Our initial value was 100, and now it was 1 minus 0.3, okay? So little r is the decimal version of big R, and that's why we use the same letter. And so this gives you a template then that you could use for any growth, any decay, as long as you know the percentage rate and or the initial amount, okay? Now here's some terminology that you need to know. All right, so if we have exponential growth, big R is called the growth rate. I'm going to call that GR for short. It's the percentage, okay? The growth rate is the percentage. Now, you can remember that because when you look at a percentage, you probably have said it before as a percentage rate. 20% rate, 30% rate, okay? 1 plus R is called the growth factor. We're going to call that a GF for short. 1 plus R is called the growth factor. So in example 1, big R was equal to 30. What was the growth factor equal to? Was it just 0.3? It was 1.3. Good. 1.3. So here's an easy way to remember growth factor. If you remember what exponential does, an exponent, is just shorthand multiplication. So when t equals 1, we have one factor of 1.3. When t equals 2, we have another factor of 1.3. When t equals 3, we have another factor of 1.3. So basically, the growth factor is essentially the what in the equation? What do we call it? In this equation here, what do we call this? The base, yeah. Yeah, it's that easy. Yeah, maybe you were reluctant to answer. The growth factor is always the base of the model. Okay, it's always the base because that is the thing that has the exponent on it. And for integer values of t, you're getting another one of those factors. Okay? Similarly, if we know it's decay, if something is getting smaller, then r is still the decay rate, and now 1 minus r is called the decay factor. So in example 2, this was example 1, in example 2, what was the decay factor? Was it 0.3? It was 1 minus 0.3, which was 0.7. Good. Good. All right? Because every time you put another value of t, you're getting times 0.7, times 0.7, times 0.7. You're retaining 70%, 70%, 70%. Okay? Cool. So let's try it out now. Very important that you get the terminology down. For the following equations, they're either growth or decay. Your job is to identify the growth or decay rates, which remember are the percentages, and the growth or decay factors, which are the bases. Okay? For each of the following. So looking at this guy here, A of t equals this. First of all, is it growth or decay? That's your first thing to look for. It's growth. How do we know? What's bigger than 1? The base. Okay, the base is 1.046, which is bigger than 1, so this is growth. Okay, so that's your first task. Now, we want the growth rate and the growth factor, the GR and the GF. Which of those two is the easier to get from the equation? The growth factor. Good. Because the growth factor is just the base, which is what? 1.046. Good. So again, that's pretty easy to determine because if you just think, keep adding an integer value of t, it's times 1.046, times another 1.046. And multiplication is a factor. What would be the growth rate? If something increases by a factor of 1.046, it increases by what percent? Is it 104.6%? No. So to find the growth rate, here's what some people find easier. If you take your growth factor and you convert it to a percentage, just move the decimal over 2 places to the right, you get 104.6%. It's a little bit easier to work with percentages because you're not working with such small decimals. All you have to do is find the difference from 100, right? So in this case, because that number is bigger than 100, just subtract out 100%, and we're left with 4.6%. And that's the answer. Okay? So what does this mean? If something increases by a factor of 1.046, it increases by what percent? 4.6%. And on the other side of that coin, if something increases by 4.6%, it increases by a factor of 1.046. Again, this is 100% everything of what it was before plus this additional amount. Okay? Very, very important. Cool. Letter B, 3 times 0.14159. Pie joke. Yeah. Go ahead and do this one on your own. See if you can get this one. Is it growth? Is it decay? If so, what's the growth decay rate? What's the growth decay factor? Good. You're identifying it correctly. What does G stand for? Growth? Is it growth? No. Good. Is it growth? How do you know? Yeah, so it should be decay. Yeah. Good. Good. You're subtracting. You know it's decay. Good. 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 DR. Yeah. Is it G? What does G stand for? Growth. Yeah. Is it growth? Yeah. So instead of G, we'll use D. You wrote it up there. You just need to use D. Yeah. We use GF and GR and then DF and DR. Decay, growth, decay, growth. Yeah, try to do this one without a calculator. Let's get some old school math going here. I see some awesome stack subtraction happening. Yeah, see, you're going to have to, oh, you want to flip it around though, right? Put the bigger number on top. Yeah. There you go. You got to do a lot of borrowing on this one. But it's good. It's fun to do this every once in a while. Okay, first of all, is this growth or is it decay? It's decay, right? The base is 0.14159, which is less than 1 but greater than 0. Okay, so it is decay. So we want to find the decay factor and the decay rate. And I wrote them in a different order this time. So we use DF and DR. Which of those two, again, is the easier to find, the factor or the rate? The factor. If you have the equation, the factor is just the what? The base. So it's 0.14159. Okay? Now the decay rate. If I were making a test, what do you think I would put as an answer choice for the decay rate? 14.159. Would you take it? No. You'd be like, ha-ha, I'm not a sucker. Right? Because we need to find the difference from 100. This basically says we're only retaining 14% roughly every time. And if we're only retaining about 14%, that means the decay rate, we are losing about approximately what? 86. Okay? So if this were a test question, multiple choice, the decay rate should be approximately 86%. If we're only retaining 14, we're losing 86. So that might be enough to go through the answer choices and pick the answer without actually computing it, right? Unless there were several that were really close to 86. And then you'd be like, Mr. Corpy. So how can we do that? Well, without a calculator, let's move it over 2 decimals. That's 14.159. If that number, which is a percentage now, is less than 100, you subtract it from 100. Okay? My battery pencil's low. Okay. So if you do this, how is it going to work? Well, remember you have to say, okay, this needs to be a 10 right here in the ones place. So you go next door. You got any 10? No. Go next door. You got any 10s? No. You got any 10s? No. Hey, you got a 10. Can I borrow one? Sure. Okay. So that becomes a 10. And now you borrow all the way down. 10, 9, okay. 10, oh, 9, okay. And then boom, right? That was fun. You have to borrow all the way down, like 4 neighbors down. And now you subtract. You get a 1. I have a 0 there. Sorry, one more. That should be a 9. So you get a 1, you get a 4, you get an 8, and you get a 5, and you get an 8. So most of y'all can handle that subtraction without a calculator. Good fun there. So it's 85.841%. So we should put a percent on the back end of that. Notice I did it over here, the growth rate percent. Over here, the decay rate percent. That keeps reinforcing it that it is a percentage. So again, the meaning of this is if something loses 85.841%, bless you, of its value, every integer value, it's decreasing by a scale factor of what? 0.14. Okay? Last one. Do it real quickly on your own. I'm going to give my pencil a little recharge here for a couple of seconds. on assembly schedule, so we're in here till 10:25. We got 7 minutes left. What's that? What are we doing? When? Right now? Oh, in the assembly? Well, it's Rachel's challenge advisory today. So you're either learning lesson 2 today, or up here in this wing, we're going to our assembly that we haven't been going to. Okay, is this growth or decay? Growth. Okay, so what is the growth rate? Is it 2? Ah, very good. What is the growth factor? 2. Very good. And the growth rate then would be what? 100. Good. So remember, 2 is the same as 200%. If you move the decimal 2 places over, since it's bigger than 100, you subtract and you get 100. So that is 100%. Now, this is something that a lot of people outside of a math context get wrong, believe it or not. Jay Leno used to go around with a microphone, and he used to do something called jaywalking. He would ask people on the street silly questions, and a lot of the times it would kind of show how ignorant or uninformed the population was. And this might have been one of the questions he asked. If something increases by a factor of 2, it increases by what percent? Guess what the reflexive answer is? 200%. Is that right? No. If something doubles, if you double a value, it only increases by 100%. If you triple a value, it increases by what percent? 200%. If you quadruple a value, it increases by 300%, so on and so forth, okay? Or if something increases by 100%, it's doubling. There you go. So now you know. All right, the last little thing I want to talk about here, we have 5 minutes. Here's a nice little application. Populations grow exponentially. It fits the criteria, right? The more people you have, the more people you're going to get. It's not true with offenses, but it is true with people for the most part, right? Because that's how people work. They procreate. Of course, some people are celibate, some people are infertile, but for the most part, that's how it works, right? Cool. So has anyone been to sunny San Jose? You have. Did you like it? Most people that go to San Jose love it, okay? Love it. By the way, San Jose means St. Joe, who's also sitting in the back of the room. Anyway, yeah, it's a beautiful place to live. More people want to live in San Jose when they visit it than not, okay? So here is a model that I pulled off of the World Wide Web. In 1990, that's a long time ago, this model represented the population. This was taken from data from 1990 to 2000, okay? So over a 10-year span, we're going to do this later, you can actually take data and fit a model to it. What was the population based upon this model of San Jose in 1990? Very good. 1990 corresponds with T equals 0. So the population was 782,248. How can you tell by the model that the population of San Jose was growing? The base is greater than 1. Good. So what would be the growth factor for this city? 1.0136. What would the growth rate be? 1.36. Yeah, when it's bigger than 1, it's a little bit easier. So 1.36%. Now, that's pretty modest growth, but for populations, that's pretty impressive. Okay, so over this 10-year period where this data was taken, the population of San Jose grew by 1.36%. If you use this model then to predict outside of 2000, that's called what? Do y'all know what that term is when you predict outside the data? Extrapolate. Yeah, that's outside the data. If you use to predict within 1990 and 2000, like in 1995, that's called what? Can you guess? Yeah, interpolate. That's going to be inside the data. Would it be wise for us to use this model to extrapolate the population of San Jose in 2018? Why not, Emma? I agree, no. How many years has it been since 2000 when the last data point was collected? 18 years. The model itself pays no attention to what's going on in the world, does it? It's just, I'm a mathematical equation. Well, what happens in the real world? Stuff. Stuff happens. Mikey's on fire today. Stuff happens, right? People can leave or we can break trends, right? Like hurricanes cause people to leave. So it's not very wise to predict so far outside the data. If we use it to predict 2001, maybe. But 2018, maybe not. Last thing we're going to do here. If I did predict for 2018, what t-value would that be? 28. Okay? Real quickly here, if I type that model into my calculator for 28, oops, you can just watch this. I get 1,141,000. Do you think that is the population of San Jose today? It's 1.03. What did our model do? It got it wrong, right? The population of San Jose is still over 1 million, but not quite by what the model predicted. Why is that? Stuff, right? Stuff. So mathematical models have limitations, right? They're good for predicting, but it's not absolute. Awesome. We'll see y'all tomorrow. Enjoy the rest of your spooky Wednesday. Dun, dun, dun. Bye-bye, bye-bye.